Oh, thank you. All right. I'm not quite sure why my iTunes is bouncing over there, so I'm going to hide my duck. Um, all right. So you're going to be doing what's called solving differential equations by separation of variables. First thing, just knowing what a differential equation is very helpful. These are hugely applicable in the, woo, I don't know what's going on here. In the real world. So this actually becomes, when we get to the second part of this chapter, there's a dead body on the front of your notes because we're going to use this in some forensic stuff to figure out time of death, just based on rates of change. So we start to apply this right here. And a differential equation is when you're given the rate of change of something, which is really applicable in the real world, but it's not given in that generic dy dx form. In the real world, when you're given a differential equation, what's on the bottom? What's the thing that's changing? Time, yeah. So on the bottom is a dt, and there's going to be something changing over time. Maybe it's in the medical field, and it's some bacteria that's growing, or maybe it's blood flow, and you're trying to do like a new medication for high blood pressure, and you're figuring out the rate that things are dilating in the blood flow, and you need to have it just right so we don't stroke out, or you know what I mean? There's lots of rates of change. Or perhaps it's population, and you know the population, and you want to figure out, not how fast or how slowly it's changing, but how much is there at any given time. And that's where this process comes in. We're going to figure out, well, how do I figure out an equation that tells me what y is? How do I figure out an equation that tells me what the bacteria is after 5 hours? How do I figure out an equation that tells me the population that's there after time t? Or how do I figure out when the radioactive material has decayed enough so it's safe for us to enter that zone again? There's all kinds of stuff like that in higher levels of engineering, the medical field. This is where it starts. You've been doing kind of, calculus is the oompa loompa of all the other stuff. It's the worker bee, but it isn't really where the cool stuff happens. It's from beyond this, and it does get applied in all economics. I had a student who's at McAllister, Brendan Farver. Did any of you know him? Graduated a couple years ago. And he's studying economics, and he had to go through Calc 2 because he's studying money, and what does money do? Changes over time. The amounts things grow and shrink, and he does integration and a whole bunch of stuff. So a very applicable skill. The problem is we can only learn one method for solving them in Calc 1. There's a whole nother class in college. It's either Calc 3 or Calc 4, depending on where you go, where that's all they learn is how do I get a rate of change and work back and figure out what's actually happening. We're going to do separation of variables, and that's the only one. And by the way, some differential equations can't even be solved, and that's where the slope field comes into play, and we're going to do those in a couple days. So if you can write your differential equation in this form, if you can write it as some function of y with respect to a change in y is equal to g of x dx, it's called separable. Right now that doesn't make sense, but when I throw it up there, you'll get what I mean by that. If you cannot manipulate it to look like this, then you can't use separation of variables. So first of all, let's decide if this would apply. On this equation right here, I am given a rate of change, and it equals x times y. What I'm going to do is take this y and move it over to the other side. So I have all my y stuff on the left. So technically I divide by y, or equivalently I'm going to multiply by 1 over y. I'm going to keep the dy there because I need all my y stuff on the left and all my x stuff on the right. So I'm going to leave the x there, and I'm going to swing this over. What I just did is called separation of variables. I'm not done by any means, but that one I can separate because, and you can go ahead and write separation of variables right here, sep of var. The reason this is called correctly separated is because this is a product. So kind of know that. This next one down here, I can't write it as a product. In order for me to move the y over, what would I have to do with it? Subtract it. That's called a non-separable differential equation. It doesn't mean I can't solve it. It means I can't solve it with this process. It needs a higher level of math. So we're going to just deal with ones that are separable. I'm going to show you how, and then we'll move from there. So this is the one on the previous page that I said is separable. And I'm chewing gum, and I'm afraid it's going to come through on my... I'm going to spit that out. So it doesn't sound like I'm this thing's super sensitive. It doesn't pick you guys up, but it picks me up like times 10. Anyway, so here's what we're going to do. My goal is to solve this differential equation. What that means is right here, I want to figure out what is y. And if that's a P, I want to figure out what the population is. Or if that's a B, I want to know what the bacteria is. But you're always solving for that top variable. It's called the dependent variable. X is called independent. X is affecting how Y is changing. Just like on the bottom, time is affecting how that bacteria is growing. So we've kind of got an independent, dependent variable going. But I want to solve this for Y. Here's how it starts. The first thing you're going to do is separate. And I just told you what that means. Everything in terms of Y on the left. So this one, I'm going to divide by Y, or 1 over Y, to get it off of that side. I'm going to keep the dy, because I want all my Y stuff on the left. The x is going to stay on the right, but then I'm going to multiply by dx to move it over. That's called separating. That's done. The next thing I'm going to do once these are separated is integrate. So I separate and then I integrate. And as long as I integrate both sides, it's legal. Anything in math, as long as you do it to both sides and you don't divide by 0 or root a negative, it's legal. All right? So I am now integrating both sides, and this is where antiderivatives come in. There won't be any really nasty ones. They'll be pretty straightforward. From last chapter, what's the antiderivative of 1 over x dx? ln. Well, this is ln, but what was there in it? Thank you, absolute value. So that's ln, absolute value of y. This one's straightforward. Usually the integrating isn't the issue. Now, what did I leave off of both sides? Carl. And technically there's a Carl on the left and a Carl on the right. But what we're going to do is subtract this Carl that you don't even see from whatever Carl was over here. And we're going to just have one Carl on the right-hand side. Because our goal is to isolate y. So whatever this Carl was over here, if it was a +2, I'd eventually -2. And so I'm just going to have some other arbitrary constant over there. And it'll work itself out. So remember, my goal is to figure out what is y. I need to undo the ln. How do you undo ln? What's its inverse? E. Yeah, it's called exponentiating. You're going to raise both sides. E to the. If you could do that, e to the ln, I'm going to keep that absolute value bar in there for a second. It's called exponentiating. E to the this is going to equal e to the that. So watch carefully here what happens next. What is e to the ln? Y. Y, that's why I did it. So really absolute value is going to I'll get rid of the absolute value soon. I have to be clever with how I do it though. Over here, I got to show you something way back from Algebra 1. Is it true that x to the 3 plus 5 is equal to x to the 3 times x to the 5? Is that true or false? True. I'm going to use that property over here to get Carl out of the exponent. So what I'm going to do is say u are really e to the x squared over 2 times e to the c. That happens frequently in these, where you're going to split it up. And here's why you're going to do that. And again, this is legal because this is e to the this plus this. So if you're wondering if that happens to you, split it up. Here's why. I want you to go like this. E is a constant, Carl's a constant. So what's e to the c going to be? A constant. And you can call it Carl with a K, or you can still just call it some other constant. But this right here, whatever C was, if it was 5, this is e to the 5th, it's some other number sitting there. So what we're going to do is say this. This is actually just some other constant. Fair enough? We'll find it later. So here's how I'm going to deal with the absolute value. I'm going to drop it right now. Are you ready? College Board doesn't mark it wrong if you just drop it. But I feel like you need to have a mathematical reason, and I'm going to tell you how I'm going to do that. I'm going to say that my big C, this one I'm going to put right here, is in actually plus or minus e to the little c. That way I can absorb the absolute value in there. So if it was supposed to be positive, it'll fall out. That's kind of just a clever way of just saying, you know what, I'm just going to drop the absolute values and let Carl absorb it. Okay, so I've got e. This right here is just some other constant, e to the x squared over 2. This right here is called a general solution. Go point at it. Here's why. What still don't you know? Like if I were to ask you, what's y when x is 7? What would be your issue? What don't I know? Carl. When you aren't given any information to find Carl, what you found is a general solution. I'm going to show graphically what you found. E to the x squared over 2 is an exponential function, and I'm going to leave it unticked. But it may be that one, but it might be that one, or it might be that one. But you know that the slope of the tangent line at 1 for all of them is the same. And it's actually equal to that original derivative. So there's a whole bunch of answers it could be. How have we always figured out who C is? A point. So on the next page, we're going to talk about, okay, who is the particular solution? Then I have to tell you a point that it starts on. 9 times out of 10 for these, it's going to be 0 because they're going to be real world problems eventually. And in the real world, when you're charting growth and decay and how things are growing or shrinking, you usually know what's there at the start. You know what I mean? At time 0. And then I've got the water tower leaking. And then the civil engineer comes in and says, you know what, you're going to lose water pressure as soon as this rate gets to here. And that means your water level is going to be to here. Do you see where that it's very applicable. Right now it seems a little weird because we're generic with the X's and the Y's, but it's coming where we're going to change this to real stuff. All right, so we already separated this one. It's the same one, so go like that. It's from the previous page. And we said that when we went through our process, we got C e to the, it was x squared over 2, right? Right? And that's called the general solution because C could be anything. But now I'm going to lock you in. I'm saying, no, it can't be. I'm going to force your curve to go through this point, which means when x is 0, y of x is 5. And you're used to calling this f of x. But in this case, it's actually y of x because that's who your function is. So we're going to go plug this in. My y has to be 5 when x is 0. That's what this is saying. So what's e to the 0? 1. So who's Carl? 5. Yeah. Carl, they're actually handing you Carl. So 5 is equal to c. So here is my particular solution. Y is equal to 5 e to the x squared over 2. And that is called solving a differential equation. If this represented money growing over time, by the way, remember the PERT formula? P e to the RT, that's where the E comes from. We derive that in Calc 2. Like, why is there an E sitting smack in the middle of your money growth? That should bug you. But you just did it, right? Because they said, but a part of you should have been going, well, where'd the E come from? It actually comes from this process, just like this one popped out an E that you wouldn't have expected, right? This formula comes from this process. We derive it next year, so not to worry. All right. So now we're going to take one off a College Board. This was off of an FRQ. I don't know what year. Every year there is one, though. It's usually your number 5 or your number 6. They have you make a slope field, which you don't know how to do yet. That's coming. It's super easy. And then they have you solve a differential equation. So we're going to start this. What's the first thing I said you do? Because we've only done one, so you should be like, what? I separate. So first thing I'm going to do is keep what I'm solving for here. So dy is going to stay on the left. This has to move over to the left. And to move it over, what am I going to do? Divide. So I'm going to have 1 over e to the y. And don't write it as divide. Write it as 1 over times. Write it as a product because it does help. I'm going to keep all my x terms over on the right. Dx is going to have to be multiplied over as well. So that is called separating. College Board says 0 out of 6 if student does not start by separating. Like if somehow you stumble upon something correct, but you don't start this way, you get 0. All right, so even if somehow, somewhere, something happens in your process, you get nothing. What did we say to do after you separate? Integrate. So I'm just going to throw it right on here. That's the easiest thing, so you don't have to keep rewriting. Now I'm going to take antiderivatives. They won't be difficult. Okay, this is e to the negative y, or e to the negative x from last chapter. Almost the easiest thing. Other than e to the x, e to the negative x is the easiest. And this over here, I'm purposely writing everything because I want you to have good notes. But this easy. What's the antiderivative of e to the negative y, dy? Negative e to the what? Negative y. We had that one a lot last chapter. It was just e to the negative x. But as long as we have a variable match, this could have been e to the negative q dq. Right? This side, super easy. What's the antiderivative of 3x squared? 3x cubed over 3, or just x cubed, minus 6x squared over 2, 3x squared. I do a double check, just do a quick derivative in your head, because one wrong move throws the whole thing off. Who have I forgotten? Carl should be on the left, Carl should be on the right, but we're just going to make one consolidated constant. All right, so always put Carl on the right. Next, I want to know what Carl is, and I kind of left off on the bottom of the previous page with something that's actually really important. It says note, if you can find Carl anytime after you integrate. Once I am done integrating, any time from here on down, I can stop and find Carl. He's not the same in every single part, but at the end he works out. It seems weird, but he does. I'll show you on the next problem. I wouldn't choose to find him on this problem right now. I like to get all the negatives and constants and everything out of the way, so I'm going to get rid of this. Fair enough? I'm just going to take the opposite of both sides. I'm going to leave Carl sitting there, and I'm going to get a negative x cubed, and then this is what bugs some people. Do you think I put minus c or plus c? It doesn't matter. And I always just keep it plus c, because if c is supposed to be 5, then if you put minus, you'll get a negative 5. And if c is supposed to be, it works out either way. So you can just go ahead and keep, it's just some other constant, and he just keeps morphing right along with it. True or false, could I go find Carl right now? Yeah. Do you wanna? Why not? I don't need to. Or do you want to wait till the end? It doesn't matter to me. That's the whole point. That's what's going to frustrate you in your groups tomorrow. Someone's going to launch into finding Carl immediately. Someone's going to wait till the end, but they should be the same. Not all the way, like Carl will morph. For the person who does it right away, Carl keeps changing with every numerical operation you do. For the person who saves it till the end, he's just there at the end. But sometimes it's harder. It's just whenever. Want to do it right now? All right. So in order for me to find Carl, there must have been a point given. Who was it? 1, 0. So when I put in a 1 for x, a 0 has to come out for y. That's perfectly legal for me to put those in right now. I like to indent when I'm finding Carl, just so I know, you know what, I'm disrupting the flow of this because I'm going to halt and figure out Carl. What'd you say? All right, you said it was 1, 0, right? So this is x. This is y. So I'm going to do e to the negative 0, which is just 0, has to equal a negative 1 to the third plus 3 times 1 squared plus my Carl. That is totally legal for me right now to stop and find him. Okay? So what's e to the 0? 1 has to equal negative 1 plus 3 plus Carl. So this is 2, and I'm just showing it all. So what's Carl? Negative 1. Okay, so Carl equals negative 1, and I'm going to go back up because I disrupted my flow just for now. I could have waited till the end, and I'm going to get e to the negative y is equal to, and I'm going to get negative x cubed plus 3x squared minus 1, and now I'll keep going. All right, how do I keep going? Who am I trying to solve for? Y. How do I undo e? ln, excellent, Annie. So all of you, but I was staring at her. So I'm going to natural log both sides. When I natural log, can I just do it right on here without rewriting it, or will it mess with your notes? I better show it just in case. So I'm going to ln both sides. All right, once I've ln'd both sides, what is ln e to the negative y? Negative y. Basically, it's negative y ln e, but it's negative y, right? Is it going to equal ln negative x cubed plus 3x squared minus 1. What's the only thing I need to do, and I have solved this? Negative both sides. Exactly, Brooke. So I'm going to have y is equal to negative ln negative x cubed plus 3x squared minus 1. The person who waits till the end to find Carl, had you waited till the end, just watch what would have happened. This wouldn't have been a minus 1. What would it have been? Plus Carl. You would have now gone and plugged in your stuff. I want you to see it, because that's what's really bugged people in years past is I don't get when to find Carl. I don't get, it doesn't matter. All right? He morphs himself. He's like Gumby. You guys don't know who Gumby is, do you? Yes, he's the green guy from Saturday Night Live from years ago in the 80s. They had a character named Gumby, and anyway, whatever. Carl Gumby. We could call him plus G. Oh, that's a new one. I've been calling the constant of integration Carl for 4 years. I think I'm ready. Ready to do plus G. Oh, shoot, I forgot. Sorry, whoever's gone and asked me to do this, I don't even remember who by now. All right, anyway, what was I doing? You're just going to watch. You're going to watch. I'm going to find him and watch how it works out the same. At this point, I'd put a 0 in right here, and I'd say that has to equal negative ln. And I'm going to erase, and you're just going to watch, because sometimes watching is better than writing. I'm just going to prove to you that it doesn't matter. Has to equal negative 1 plus 3 plus c. Correct? This is 2. ln of what is 0? Because the negative doesn't matter. 1. What will make this be ln of 1? See what I mean? He works himself out. All right, so next page. I'm going to stop right here for a second and stop the recording because I'm going to do that.